department lecture Fridays. I am not actually part of the history department, but I'm glad to be able to present in part of this series. Today I'm going to be talking about image manipulation using computational algorithms. This presentation is designed basically for an absolute beginner. So if you've never done programming, don't worry. We're not going to focus really on the technology or the syntax, just the concepts of how programs are actually made and what they do, etc. So if you can follow along with concepts such as get or set something or average something or do something if, then you'll be able to follow along just fine with this lecture. So it's mostly concepts related to key things that programmers would do on a regular basis within computer science. So with our learning objectives, the first thing we want to do is to look at how computers interpret information, how they can manipulate and process that information. And in order to do that, we need to break this down into several sub-steps. So number one, we need to understand computational algorithms. And that's basically the process that a computer is going to do in order to solve a problem. The next thing we need to do is to understand different functions. So this starts getting into the structure of a language. And we're going to be looking at how to get or set information, for loops, average, and ifs. Okay, so do something if. Okay? So these are all different types of statements that, from an English standpoint, are quite common and easily understandable. And they have their own specific syntax in the programming language. Finally, since we're going to be looking at visual examples, we're actually going to be creating programs and discussing programs about how to manipulate images. We need to understand how computers actually understand images. So we're going to look at both pixels and 8-bit color. Now, throughout this presentation, I've started with the big ideas and worked my way down to smaller ideas. So in the presentation, we're actually going to work our way up the list, starting with the smallest aspects and then working towards the big idea, which is to create a program to do what we want to do with it. So in programming, we'll often use this idea of backwards design. Start with what we want to achieve, and then work our way backwards to figure out how do we achieve that. So the first thing that I'd like to talk about in this presentation is color theory. So this gives you a very quick introduction to the science of color. Not an artistic expression of color, but an actual mathematically sound understanding of color theory. So the first thing I want you to think about is, what are the primary colors? So can I get a volunteer from someone who hasn't read the lecture notes? Bill?
Yes.
Okay, so what?
Red, yellow, blue.
Red, yellow, blue. Okay. So red, yellow, blue is what is taught in schools. But red, yellow, blue are actually not the correct primary colors.
What?
So red, yellow, blue is a common misconception. It is what is taught in schools from primary. It's been taught since the age of Leonardo da Vinci. But we've actually known better. We've actually had a scientific understanding of color theory since the days of Sir Isaac Newton. Now, color theory is actually a lot more complicated than what they teach you in kindergarten. So there's not just red, yellow, blue. There's actually two different sets of primaries, and each set has 3 colors. Now, before I get into each of those sets, we really want to think about how do we perceive colors as humans. So color is a result of light. Okay? So light will hit an object, and that object will reflect light back to our eyes. Now, depending on the color of that object, we might receive red light, we might receive yellow and green light, we might receive blue light. Now, we have different aspects of how energy is either absorbed or reflected or transmitted through objects as well. So there is a lot of physics involved in the study of color. But if we really think about it, we really need to think about color as both a function of energy, but it's also a function of matter. If we do not have light, which is a form of energy, we cannot see color. If we do not have matter, we have nothing to reflect that light back to our eyes. So we have these two aspects of both energy and matter. But anyone who has heard anything from Albert Einstein, equal mc squared, Energy and matter are complete opposites to each other. And for that reason, we have two sets of colors. We have additive and primary. The primary colors of matter and the primary colors of energy or light. So we have two color systems in total. And we need to think about both of these color systems when we start getting into a scientific understanding of color, and also trying to represent those colors with things such as a TV screen or a computer monitor, which is going to be using light, or if we're going to be using a printer to print an object, in which case we're going to be using matter. So the additive colors are red, green, blue, RGB. And you've probably heard this acronym quite a lot, RGB. If you've done anything with stage performances, you have RGB lights. If you look at buying a TV, they often tell you about the RGB pixel count, etc. So these are our additive colors of light. So we have red light, blue light, and green light, and they add together to become brighter. Okay, so if we have red and green light, we'll actually get a brighter yellow color, which is the exact opposite of what would happen if you had paint. If you mixed red and green paint, you would get brown, which is darker. Okay, so it works the exact opposite. Now, if you have all three colors of light, you end up getting white light. Okay? And you can separate that back through prisms. And the first person to really understand this was Sir Isaac Newton, when he started doing research on diffractive optics using prisms, separating white light into multiple colors, and then joining it back again. Now you can also see this in your computer screens. If you look very closely at the screen of your computer, you'll actually see red, green, and blue pixels. And depending on what color you have shown on the screen, different pixels will be active. Now the subtractive colors are cyan, yellow, and magenta. Now the subtractive colors subtract to become darker. So if we take yellow and cyan, when mixed together, they will subtract to become a darker color of green. If we take all three colors, we'll end up getting black. Okay? And this starts kind of settling this idea of, is black or white a combination of colors? Because you often have this argument within students in school. Oh, white is a combination of all colors. But then people say, but no, black is. Billy, you had a question?
Yeah, sorry. What are you subtracting exactly? Are you removing, so is you remove something that gets darker, or is it a mix?
Yeah, so when you have yellow,
right.
Yellow is going to reflect yellow light.
Sure.
When you have cyan, it's going to reflect cyan light. When you mix these together, the cyan is going to subtract some of the yellow light that's reflecting back to your eye. So what happens is, as we mix more colors, we keep subtracting the amount of light reflecting until we have black, which is no light is reflecting to your eye. So when we look at the color systems, additive colors, they add together to become brighter, because the more energy we add together, the more energy we will have, and thus a brighter color. And subtractive colors do the exact opposite. The more subtractive colors we mix together, the darker it becomes, because each time we mix a new color, it will subtract the amount of light reflecting to our eyes to become darker. And you can see this in your color printers. You have cyan, yellow, magenta toners for your laser color, cyan, yellow, magenta blackies for your inkjet printers. So the entire industry knows the correct primary colors, except to this day, education still teaches color theory inaccurately. So there is a really big science behind color, and as programmers, we need to understand the science as we start building programs. Now the next thing I want to talk about is how do we represent colors digitally. And in order to do that, we use binary and hexadecimal. We use a number of codes to represent each color that we can create using the computer. Now computers represent color using what is known as 8-bit color. Okay? And you might have heard this term before, 8-bit color, or potentially even 12 or 16-bit if you've looked at very high-end equipment. Now, it's pretty easy to kind of get the big idea behind this. So, 8-bit color uses 3 hexadecimal couplets. Okay? So a couplet is a combination of 2. Now, each of these couplets represents the amount of red, green, and blue light. So each couplet is telling the pixels in the computer screen how much light to present. Now, the first 2 couplets tells you how much red is in the combination. The next 2 tells you how much green. and the last two tells you how much blue is needed to create color. Now, since each hexadecimal pair is equal to 8 bits of information, we get the term 8-bit color. Now, since a hexadecimal couplet can represent up to 256 values, okay, and this is getting into a lot of the math behind binary and hexadecimal conversions. So I won't get into the math behind how we get to 256. But a hexadecimal couplet can represent 256 combinations. So that means the computer can represent 256 combinations for red, 256 combinations for green, and 256 combinations for blue. Which means if we take 256 times 256 times 256, that gives us 16 million color combinations that the computer can represent and show us to the human eye. Now this is far too many colors for us to give names to: cyan, indigo, azure, etc. So computers do not use color names. We use numerical codes, which are made out of a 6-digit hexadecimal code. Now this is just a quick representation. If we graph all these colors in a 3-dimensional space, you can actually see a visual representation of 16-bit color. And using mathematical algorithms, we can even compare and contrast. What we're seeing is now what a standard computer monitor can project based off of what the human eye can perceive. Right now we're actually graphing web-safe colors in comparison to what the human eye can see, etc. And by actually analyzing and graphing, we can even simulate things such as colorblindness, deuteranomaly, protanomaly, tritanomaly, etc. So there's a lot of really interesting things that we can do once we have a mathematical understanding of colors. Okay, so now that we understand how we can represent colors as a code, now we need to think about how do we represent a picture. So in computer science, it's not enough just to understand the programming. We need to understand how the programming relates to all sorts of different fields of study. Now, in this presentation, I'm going to go through a series of manipulating images or pictures. But the same principles could apply to manipulating sound, to manipulating videos, text, etc. Okay? So, in order to do all sorts of manipulations, we use different programs. And each program has a specific function. So we have things like Photoshop to manipulate pictures. We have things like Premiere or iMovie to edit videos. Or we have things like Audacity for sound. Now, what we're going to look at is what's happening behind the scenes in those programs. What is the computational algorithms, the math that's happening to create those different effects. Now, to first do this, we need to understand how a picture is created. Okay. So we understand color now. We have these hexadecimal codes, but the computer doesn't understand a picture. So we need to create a way of the computer to understand this visual information. And to do that, we need to first create a grid. Okay, divide the picture into a horizontal XY axis, and this is going to give us a series of pixels. Okay? So here I've divided an image into a grid. This is a very simple grid, 10 by 10, nothing too fancy. So if we look at this, we have a 10 by 10 grid, which would be a 100 pixel image. Now, when you look at your current smartphones or cameras, you know, your iPhone maybe being 8 megapixels, or Sony has a 40 megapixel camera phone, that means you have 40 million pixels. The more pixels you have, the more detail, the more information you have in your picture. But regardless of the size of your camera, the resolution, the concept is the same. Whether or not you have 100 pixels, 100,000, or 100 million pixels, the concept is the exact same. Now, each pixel has its own location, and in computer science, we actually assign locations a little bit different than you would in math class. And normally in math and science, we would go left and then up for our X and Y axis. In computer science, we actually start in the top left-hand corner and not the top bottom corner. So we go with an XY value, and we read top to bottom, left to right. So how we read as humans, we would start in the top left-hand corner and read across. And we've created computers to follow that same logic. So when we assign locations in computing, we follow the same logic as we as humans follow when we read. So the yellow pixel, for example, is at location 0, 0. And the blue pixel, James, where would the blue pixel be, for example?
9, 9.
Location 9, 9. Okay, so it's pretty easy to read the grid once you know the structure. Now, programs that handle and manipulate images use commands. Okay, so we call them program statements, but they're just commands that tell the computer to do something. Okay? So here I have a little bit of Java. So I have image equals new simple image x.png. Okay? So any idea what this little bit of program code is doing? Bill?
Yeah, if you go back to your older Cartesian plane, it's communicating those coordinates onto like that bottom left. Like, so like, okay, it's like 0, 0, 3, 1, 4, 2, and then you got like a whole cluster in the middle that goes, yeah, it's communicating that Cartesian schematic that you showed it.
Good, okay, so we have an image, and this image has been broken down into a plane of pixels, so a 100 pixel image. So we are communicating information, but essentially what we're doing is, in this command, is we're saying image new. So we're basically saying file new. And we're saying x.png, so it's a file name. So this particular command is saying open the image x. Okay. So I've now done open the image x, image set zoom 20. And what did you see just happened there? So what do you think this next line of code, image set zoom 20?
20 times bigger.
Good, make it 20 times bigger. So in Java, it's actually a base 10 hex denary system. So image set zoom 10 is basically just 100%. Image set 20 would be 200%. So basically it's going in multiples of 10% for each value that we have. So if I change this to image set zoom 30, what would happen? It'd be bigger, okay? So image set zoom 30, so 300%. And if I did image set zoom 40, it is now 400% bigger. So pretty easy, just load image and then zoom in 40%. So not overly difficult what's happening here with these commands. Now here I have a new one, so pixel, image get pixel 0, 0. Okay? So I'm saying get pixel at location 0, 0. Okay? So Bill, what do you think this line of code is essentially doing?
Well, it's going to coordinate with your top left pixel, right? And then it's going to turn it red.
Okay, good. Okay, so it's saying get the information for pixel 0 and set that pixel to be equal to red. The next thing we do is to print or to execute that command, and this line of code has now altered that one pixel to become a red pixel. Okay? So pretty easy what's happening, even without having a background in programming. You can basically deduce what's happening in this program just by looking at it logically step by step. Now, handling each pixel, especially if you have 40 million pixels, is not very practical. So we need to find ways to do this more effectively. How to handle every pixel in the image simultaneously. So to do that, we have what's called loops. Okay? So loops are basically just telling the computer to continue to do something until it cannot do it anymore. Okay? Keep repeating that instruction until you've done it to everything. Alright, so here we've done a slight modification. So we've said load the image X, and 4 pixels in the image, set the red to 0, set the green to 0, and set the blue for 0. So it's basically going to say for every single pixel. Now when we hit print, it turns the entire image black instantaneously. Alright, so at first glance, just might say, well, why would I want to do that? This is pretty pointless. Why would I want to overwrite my beautiful X image with nothing but black? Yes?
Can I guess?
Yes, you can guess.
Is it, okay, maybe I'm totally wrong here, but is it because like the printing process itself subtracts the black? Because it's like less computation power to subtract, so like the black squares and then leave kind of like the resin there to print it out. Is it kind of that?
Good idea.
Okay.
But essentially what we're looking at is we're building up a program in baby steps. So we have created a command, we've bumped into a problem, so we have something that's viable, but we need to tweak it to give us something a little bit better, something more usable. And this is what happens in programming, is this constant kind of back and forth between writing code, testing it, analyzing the results, and then figuring out what we need to do to modify those results to get what we really want as a final outcome. Okay, so here I have another image. So this is a much more complicated image. And basically I have the exact same bit of code. So I'm saying for every pixel in the image, set the green to 0, set the blue to 0. Now, what do you think is going to potentially happen when I execute these commands?
Maybe black.
Maybe it'll be black, okay. Now when we got black, I set red, green, and blue to 0. Now in this case, am I setting red to 0 as well? No, just the other two. So, okay, so let's take a look at what happens. Right, so every value has been set to 0 except for the red 0 values, which have been left alone. Now this gives us something much more interesting than in the last example. So in this sunset example, everything that was blue has been removed from the image, everything that's green has been removed from the image, and anything that was red has been left alone. And this has given us a very red-looking image. Now, in computer science and in photography and graphic design, this is called the red color channel. And if anyone has done any Photoshop editing, you might have gone into your channels and you've played around with the red, the blue, or the green color channels to edit your photos, whether or not it be vacation photos or professional photographs that you've taken. And this is exactly what Photoshop is doing when you're adjusting the red, green, and blue channels individually. Okay? So people like graphic designers, web designers, and artists will go in and they will manipulate images based off of color channels. They may not understand the programming or the science of what's happening, but this is what's happening behind the scenes. That is the program, the code, that they're actually adjusting without even knowing it. So if we take a look at this image, we have red, green, and blue channels all active. We could isolate the red channel, the green channel, or the blue channel to analyze the different levels of colors throughout the image. Now we can increase the power of this loop by adding some expressions. So each step we're going to be building up the program, making it a little bit more sophisticated. So we can get commands such as print value. Okay? So print value is just going to tell us the value that's there. Okay? So it's giving us information that is static. But we can also go a little bit further and get expressions. Now expressions can modify information. Okay? So we can get values, we can add values, or we can modify values. So in this case, rather than saying just get the information that's there, we can say get the information value plus value. Okay? We could add information together. Okay? So in this case, we have this program code. And in Java, if you want to write a comment to the programmer, but has nothing to do with the program itself, you can notate it as a //, and this just becomes a comment to a programmer. Okay, so I have this code here, old equals pixel get red, and then I have a new line of code, pixel set red, old times 2. Now, any idea what is happening in these two lines of code? So I'm basically saying get red, and then set red, old times 2. So what do you think is happening in this bit of code? You're making it redder, okay? Alright, you're doubling the red value. Okay, so whatever red was, if red was 1, okay, that's the old value for red, and we're doing red times 2. So the new value is going to be 2. Okay, so we're doubling the pixel's initial value. So let's take a look at this a little bit easier. Within programming, okay, we can do things in multiple different ways. So here we have it in 2 lines of code. You could also simplify that into a single line of code, saying set red to get red times 2. Okay? So you can see same semantics, same logic, but just more elegant. Okay? And this is the difference between a novice programmer and an elite programmer. Someone like Wolf would probably be writing code like this, where maybe on my first lesson I'd be writing simple code like what's on the top. Both will achieve the same thing, but this will do it in 1 step rather than 2, saving your computer's processing power for other tasks. Okay, so I'm going to use this new modified code. So I have pixel, set red, get red times 2. Print the image, and what do you see happens there?
Right. Yeah, it's more lush.
It's more lush. Okay, so this image was predominantly in the reds. I didn't want to affect the blues. I wanted the water to stay the same. So I've made the red channel a little bit brighter, and it's just made those colors pop a little bit, made it a little bit more lively. Okay. And I didn't have to go through pixel by pixel. Okay. The program is going through the entire image and continue to do this operation until it reaches the end. So that brings me to this idea of loops and averages. So we're going to make these commands even more powerful by adding averages rather than just get and set information. So we've looked at color images, red, green, and blue images, but what about black and white? How would we make a gray image with tones from pure black through grays to a white if all we have is color? Any ideas how we would make gray on a computer? Think about what happens in art class when you start mixing all those colors together.
Well, they all get black. So you subtract from black.
Okay,
Yeah, and then exactly.
Okay, so subtract from black. So basically what happens when we start mixing these colors is they muddy the other color out. So we start getting tones of these neutral, dull colors. Okay, so if we set the red, the green, and the blue values to be equal to each other, we'll get a gray. And the reason for that is if we have all 3 primary colors and we mix them in equal proportions, each color is going to neutralize its opposite. And by neutralizing its opposite, we are left with gray. And if we put 100% of all 3 colors, we have nothing left, we end up getting black. Okay, so in this section we're going to take a look at grayscale images and how we're going to be modifying those codes to understand a very nice artistic expression of photography. Okay, so far I've been using this expression 4-pixel image, which is not actually the real syntax for Java, but to make the beginning of the lecture a little bit easier, I simplified it. The true structure for Java is actually this: for I in image, pixel equals image I. And I'm not going to go into the semantics of the structure, but from now on I'm going to use the real syntax that the Java programming language uses. Alright, so before I gave you a simplified, a cheating expression, now I'm going to give you the real expression as we move forward. Okay, but essentially it does the exact same thing. Okay, so this image here only has a red channel in it. Okay, so how would you propose converting this from a red image to a gray image? Bill?
I don't know. I don't know anything about it, so I guess, can you, superimpose one channel onto the other to get like a gray tonality?
Good, okay, superimpose different channels on each other. So
right, is that it?
in order to neutralize, we need equal red, equal blue, equal green. So we have red already, and we need blue and green to equal the red. So we need to basically superimpose equal values for red, green, and blue.
Which will get a gray.
Which will give us gray.
Okay.
Okay, so in this case, all we have to do is pixel, set the green, get red. So set green equal to red. Set blue equal to red. Okay, so we're basically superimposing the information from the red channel onto the other two channels. When we print image, we now convert this to a beautiful black and white image, probably somewhere nice Colorado, etc. Okay, so this time, different image. I'm going to get you to modify the code. Okay, so how would we change the code to this, to make this a gray image?
Well, set red equal to blue, set green.
Good. Okay, so in this case, we have blue, so we just modify which values we're changing. So we set red equal to blue, we set green equal to blue. We don't need to set blue because we already have it. And this gives us a nice boardwalk, probably down in California. Alright, but how would we convert a color image to a grayscale image? Okay, so this becomes a little bit trickier. Alright, so what would you do? Would you take the red channel? Would you take the blue channel? Would you take the green channel? Or would you do something else? Dwight, any ideas? So it was easy when we only had a single color channel, but now we have all three.
Do you subtract channels and then you set it and do like reverse engineer? Do you subtract channel and then you could?
So maybe a subtract.
Oh no, I mean I'm really just.
No, that's what we need to do as programmers.
I'm just freestyling here.
You set them all as equal?
Good. We need to set them all as equal somehow.
Yeah, that's the trick.
All right. So in the first example, what I'm going to do is I'm going to try isolating a single channel. Okay. So we're going to use the same method as what we did in the previous image. That worked. Okay. So set green equal to red, set blue equal to red, and we get this. Does this look natural?
It's a photo negative.
It looks like a negative, so not what we really want. Alright, so let's try setting the red equal to green, the blue equal to green. We get that. Still not what we want. Set red equal to blue, set green equal to blue, and we get that. Okay, so in this case, when we have all three channels, we can't just use the information from a single channel to superimpose onto the other channels. So it worked in the previous images because we only had one channel. It doesn't work in this image because we have three active channels that we need to consider. Right, so selecting only one channel does not do what we need. So we need to think about how do we address this problem. Now here I have a table, and we can think of colors in several different ways. Okay, so I have these different colors, and in this color, you might think that the red is the brightest because it's the biggest number. But if we take an average of all these colors, the brightest color is actually the bottom one. So we can think of not colors as individual combinations of red, green, and blue, but we can think of colors as a tonal average of all the colors. And this starts to bring us down to more what someone with monochromaticism or colorblindness would see. Okay? They wouldn't see individual colors, they would just see the progression of colors from white to black. And that's what we need to think about here, is not looking at color as a color, but as a tone, landing somewhere between white, which is 100% light reflecting to your eye, or black, which is no light reflecting. Okay? So we have to think about how would we write the syntax for this. Okay? So we need to find an expression that would find the average. Okay? So an average, we all know how to do averages in math. Basically just add up the 3 and then divide by 3. So in this case, what we've done is we've created a new variable. We've said average, red plus green plus blue divided by 3. And then when we set the red, we're saying set red equal to the average, green equal to average, and blue equal to average. We execute the command, and we get a nice black and white image that has considered all the tonal values. I'm going to speed up a little bit. So that brings us to logic statements. Okay. So logic statements can create really complex and powerful commands. Okay. So we have things like ifs and loops, and those are the two that we're going to talk about in the last examples. So in this case, I want to do this really cool thing where I want to change the color of that stop sign. I don't want it to be red anymore, but I don't want to affect the rest of the image. So in here, I've gone in and I've said, get red, and if red is greater than 200, set red to 0, set green to 0, set blue to 0. Okay? So I'm saying if the red value is over 200, make it black. Okay, so do you think that this is going to make my stop sign black?
I'm going to think the photo negative thing, right? Aren't you getting the same column?
Okay. So I'm qualifying has to be greater than. So I execute and the sign does go black, but a bunch of my clouds also go black as well.
Because it's the same white as the letters.
Good. White has a lot of red in it. It has a lot of blue and a lot of green. So in this command, it is too vague. Okay? Other colors qualify for this expression. So we need to improve this expression a little bit in order to make this work. So because multiple parts of this image qualify, we need to narrow and focus our expression down. Okay? So this is where an if statement becomes quite useful. Okay? So we're going to use the if statement to improve this command to target only the red and ignore things like the whites in the cloud. Alright, so if we take a look at this example here, we have 3 groups of colors. Okay, the first one, if we take a look at the average, and it is a bright color because all the colors are approaching 100%, but it's predominantly red. Okay, the second color is predominantly green, and the last color is predominantly dark and is mostly blue. Now we can see that this particular color is very much red. Okay? The red is way over the average, where this one right here, the blue is just slightly over the average. I'm going to come to this point in just a moment. So here what I've done is I've created an average. I said average, get red, get green, get blue, divided by 3. And then what I've done is if red is greater than the average, then change it. Okay? So that's going to start eliminating those blues that have a lot of red in them. But I've also done this. I've said average multiplied by 1.2. So I don't want it to just affect the things that are only red. I want to make sure that they are well above the average so that I don't get any accidental clippings or anything accidentally coming from the cloud. And I can tweak this number until I get it perfect. Okay, I can try average, I can try average 1.5, and I can adjust this number until I get the threshold perfect to give me what I want. When I execute this command, I now have changed the color of just that stop sign and not the rest of the image. Alright, so we can take this a little bit further, and I am speeding up quickly because I know I was supposed to be let you guys at 5. So in this particular image, we have this picture of this guy plowing his fields. And it's beautiful, sunny day, blue clouds. And I want to adjust this. I want to select those blues and make that sky look like a gray, overcast day like it is outside. Usually you want to do the opposite, but just for fun, we're going to take his lovely French vineyard and turn it into a gray, gloomy day. Alright, so I did the exact same thing in my previous image. I said, set the blue, okay, if it's greater than the average times 1.2, set the red, the green, and the blue to a value of 120. Okay. And I ended up getting this horrible looking image. Alright, so what happened in this case?
Well, there's no gradient.
Good, there's no gradient. I just arbitrarily assigned the same gray value for anything that met that expression, rather than taking into consideration the subtle differences in all those blues. Okay? So our loop statement, or if statement, didn't do what we wanted. It wasn't very flattering. Now, as a side note though, we created something called posterization, where we create this effect of minimizing to a single color. And posterization can be a very desirable effect for an art teacher, particularly in graphic design and pop art. And posterization, you probably know Andy Warhol. these are examples of posterization, very famous artworks. So although this was a mistake for our purposes, it can be used for desirable reasons in a different context. Okay? So I don't want to just rule it out as a mistake. We've accidentally discovered something that could be useful in a different situation. So in that case, we take that, we put it in our tool pocket, and we keep it for another job. So we need to improve our if statement so that we can avoid posterization for this image. So how can we assign a better if state value to this if statement? Yes?
Well, can we just do the same thing with your with your decimals, and then you tweak the numbers? Can you do the same thing?
That will tweak the threshold, but not tweak the tonal gradients. Right, so we want to think of each individual color as what? Colors are made of a combination of red, green, and blue.
Yeah. Well, no.
So rather than assigning one gray color for each, we can take the average. So take the average that's already in this image. All right, we created an average up here, so let's just use that function already. Okay, so we're going to set the blue if it is greater than the average, and we're going to set the red equal to the average, set the green equal to the average, and set the blue equal to the average. And now we've targeted just the blues, and we've converted the sky to this gray, cloudy, gloomy day. Okay? So we didn't actually even need to create a new variable. We already had the variable in the program ready to go. We just had to use it. All right, so very last example. This is where it gets really fun and exciting. Green screen.
Sorry, Scott.
Yep.
Just go back to the picture.
Yep.
Like, you wouldn't just leave the picture like that because the light and the rest of it would be, you wouldn't get that light if it was that kind of picture.
No, it's you have very high contrast light, which you would not have on a gray, cloudy day. So within Photoshop, then you would have to go in and start setting up masks. But then that's getting into manual intervention within photo manipulation. So right now, I'm just looking at the program codes of what's happening when you do an automated task. I'm not going in and manually touching up certain areas. But very good catch on that. This has not addressed lighting issues that we've now created without taking that into consideration. Very good, James. So the last one, green screen. So let's take a look at what's happening in green screen. We have a beautiful green screen room next door. So how do we create a program that does that? Okay. So green screen is called Chroma Key, and we can either do Chroma Key with blue or green. These are the most common. And basically what we're doing is we're making part of an image transparent based on its color. Okay. Now there's our definition of Chroma Key, but I'm going to skip over since we're a little bit late. So in order to create Chroma Key, the first thing that we need to do is have two images. And this is the first time that we've done two images. Up until now, we've only been working with just one. Okay. So a little bit more complicated, and this is our final example. We've been building up to this. So the first thing we need to do is to first overlap the images. Now we can't see the newsroom anymore, unfortunately, but the information is still there. Now what we need to do is we need to set the foreground to be equal to the background. Okay, so we basically need to pull the information from one image and overwrite with the other image. And that's what's actually happening is we're actually not making the green transparent, we're actually overwriting the green with the information from the previous image. Okay? Alright, so what happens next is we need to assign color values from one image to the other image. Alright, and I'm going to kind of jump ahead. So we have this block of code, and basically what we're saying is image, new symbol image, news anchor. Okay, so we're saying open the image news anchor, which is him. Next we have back equals new symbol image, newsroom. So we're opening a second image, and we've placed that in the back, in behind. So that's fairly straightforward so far. We've now gone in and created our for loop, so 4 pixels in the image. And we have average, okay, so average the red, the green, the blue, divide by 3. And if the green is greater than the average, And we set a threshold of 1.5 because we might have a little bit of green in this tie or a shirt. We don't want that to accidentally become transparent. So we've set a threshold fairly high so that only that green is selected to change the information. Now, we need to be fairly specific though, because we need to get each pixel from the previous image to this new image in the correct location. So the first thing that we have is this x equals pixel get x, y equals pixel get y. So we're saying get the location of x, get the location of y, and that will give us the xy location for every pixel in the previous image. We're now going to say pixel 2, so we're going to create a new variable. So pixel 2 equals the back get pixel. So this new pixel is going to be equal to the information in the back image for x and y. Okay, so we have this variable called xy, which now consolidates the x location and the y location for every pixel in the image that we cannot see currently. We now have pixel set red equal to pixel 2, set green equal to pixel 2, and set blue equal to pixel 2. So we're basically saying set the red, green, and blue for all of these green pixels to be equal to the information in the pixels, the corresponding pixels in the previous image. So there's the code a little bit bigger. And I'm going to skip ahead. So when we execute that, we end up getting our final newsroom. Now in video, this is happening at potentially 60 frames every second. So you can imagine how much horsepower that computer is pumping out to be doing all of these calculations for millions of pixels at a fraction of a second. But that's what's happening behind the scenes. So this is what, as computer programmers, this is what we're doing is when we're designing programs to do all sorts of different aspects. And there's three main domains within programming. We have this conceptual domain of trying to figure out what we need to do, which is what we've looked at today. We have the syntax, which is the structure of the language. And then we have the technology, which is your computer and your IDE, the software that you're using. And each domain is all interlinked. So what we end up having to do is we have to learn a little bit from one domain, go into the other domains, and we have to keep circling back and forth. So today I've omitted the syntax, I've omitted the technology, but hopefully I've given you a good visual representation of what programming is all about and the type of challenges and the way that we go about solving those challenges using math, by using various algorithms to calculate and manipulate data. So thank you very much. Sorry for keeping you guys late. I hope you enjoyed. And there's still some coffee and tea if you would like.
Good stuff. I like it. Honestly, yeah, just wanted to know the background in programming, like at all. It was so accessible to me. You know what I mean? It's like it was like I see like the.
I tried to keep that as visual.
Yeah, thank you. Because like I'm not. This isn't like my strong suit, but it's.
You've got that Asperger's going for yourself.
I do know.
Thank you so much, Scott.
Thank you, guys.
Yeah,
Think I'll take this? Yes.
You should